Okay, so I wanted to talk some more about the substitution rule. As I said, it's pretty important. Hopefully, the examples we've seen so far kind of get that point across. It really does open a lot of doors for us in terms of how to evaluate either indefinite or definite integrals. The real key that ends up coming up when you're doing this, um, taking a derivative, you might say, I'm flashing back a bit here, but taking a derivative you can kind of describe as like a science. It's almost a flowchart thing. Once you have the base formulas in place, given just about any typical function you can imagine, you can sort of work through, well, all right, do I see a product? Do I see a composition? You can work it out in terms of how the rules end up applying. Working out integrals, unfortunately, it's less of a science. It feels like it's more of an art. It's the sort of thing that, when you've been at it for a while, you kind of build up some muscle memory of sorts for how to do these things. Substitutions really end up kind of lying at the heart of that. And the real key to making sure you know how to execute a substitution and work out the resulting integral is figuring out how to choose the u. You'll often hear me you'll hear people refer to these as u substitutions or just u subs after you've been at it for a while. Picking that u is really important. If you do it wrong, you just end up making things worse. If you pick it right, then it collapses down really neatly once you get all the pieces in place. So the examples we've looked at so far tended to deal with two main ways to pick out our new variable u. So we could look for something that's inside a set of parentheses, like a trig function or something being raised to a power, that kind of thing. Or we saw several examples where stuff living underneath a radical, because that's really just stuff in parentheses again if you turn the radical into like a fractional exponent. There's a couple of more big categories I wanted to mention. We'll fill in blank number 3 here. It's going to be a bit before we get to number 4. He's kind of important to me, but anyway. So the thing we're going to zero in on here is if you've got an expression that looks like a fraction of some sort, the stuff in the denominator of that fraction is often a really, really good target for your u substitution. So that's where we're going to fill this in. They said we'll get to number 4 if you just want to leave a blank spot in your notes to fill it in later. Whatever. We'll get back there. For now, let's take a look at some examples of how to use this denominator stuff, and then we'll get rolling. But there's stuff all over this board. That's a pain. I hate jump cuts, but it's hard to deny their utility. All right, so let's take a look at an example here. All right, so the guy I want to look at is the following. So we have 3x over x squared plus 1 living inside this indefinite integral. The same process would work for definite integrals, but we'll stick with indefinite stuff just so you actually see how the substitution flows. All right, so we can't really do anything about this with like regular algebra moves. So here, following what I just suggested, let's grab the denominator of this thing, call that our u. Now remember from before, once we pick out a u, the very next thing we do is to work out the corresponding du. So the derivative of x squared plus 1 is 2x, so du is 2x dx. Looking around in here, following the protocol from our previous worksheet, well, we see an x, we see a dx. We don't have a 2. I mean, we've got a 3, I guess. So I'm going to go ahead and pull that 3 out front. Following what we've done before, we've got something like that. 1 over x squared plus 1 times x dx with the 3 held out front. Surprise, surprise. Divide both sides of this thing by 2. And I get 1/2 du equals x dx. Now I can execute my substitution. This just becomes 1 over u. X dx, we said, is 1/2 du. The 1/2 is constant. He can get held out front. So we got 3/2. So now that's gone. Our antiderivative that we need is just 1 over u. Don't try to use the power rule on this, u to the minus first. If you try to use the regular power rule, you divide by 0. That's bad. Nobody does that. So, well, for our purposes, nobody does that. Anyway, the antiderivative we want here is, in fact, the natural log function. So remember those absolute value bars that appear on our bestest friend formula? They're important. This could technically be, negative. So you get the idea. Anyway, so now we have to undo the substitution. This isn't a definite integral, so we want things back as a function of x. So we have 3/2 natural log x x squared plus 1 plus c, and that is the answer final. All right, so there's one example of this in action, grabbing something out of the denominator of an expression. So this is the first problem on a worksheet that you'll see posted in Moodle with a fair number of these problems where we really zero in on this whole denominator thing. So if you want to go ahead and go grab that, that's great. I'm going to hop over some of the examples and leave them for you to work out, but I do want to take a look at a couple more of these guys. So bear with me for just a moment. All right. This one is a little bit tricky, and on some level, if you look at the worksheet, I actually think this problem is probably the toughest of the whole bunch that appears, but we'll get through it. So looking at this guy, we've got one polynomial divided by another. Following the principle I've laid out before, let's grab that denominator, u equals x plus 1, and see what happens. The good news here is that the du and the dx are pretty clean, because the derivative of that substitution we got there is just 1, so du is just dx, which means this just swaps immediately. That seems nice. This is now u. The problem is we got to figure out how to turn that quadratic polynomial up top into something in terms of u. So here's the way I'm going to do that here. I'm going to take this substitution, u equals x plus 1. I'm going to solve it for x. So it doesn't take too much. Algebra-wise, I just subtract 1 over. So I've got x equals u minus 1. Now that turns this thing. So the u and the du are already anchored in place. This is going to be u minus 1 squared minus 3 u minus 1 plus 2. All right, so we've got some algebra to do here. Sorry, there's not really a way around that. So once I pound out all the algebra, I get up top u squared minus 5u plus 6. Still have the u down below. Got my du right there. All right, remember, we don't have a quotient rule. I'm going to have to break this thing up into 3 separate terms, each divided by u. When I do that, that's going to leave me with u squared divided by u is u, minus 5u divided by u is just negative 5. Then we have 6 over u in the back. Each one of these we can work out fairly painlessly. So I'm going to come over here. So let me cordon this stuff off so it doesn't get too confusing. So we have 1/2 u squared from the first guy minus 5u from the second. I skipped over the 6. It's important to keep him around. 6 ln absolute value of u plus c. Now I need to undo the substitution, right? So now I got to try to fit this into this little bit of board space that's left. Sorry if my handwriting gets bad, but oops. It should be a minus 5 times this thing. Okay, so we have 1/2 times x plus 1 quantity squared minus 5 times the quantity x plus 1 plus 6 ln absolute value x plus 1 plus c. And that's my answer. All right, so I will put the official "this is done" box around this. You might be saying to yourself at this point, Self, was all of that algebra necessary? Technically, no. Another way you might have tried to go about this was hop back up to this bad boy right here and do polynomial long division or synthetic division to take this thing apart. Yeah, that's what I figured. Just about everybody, when confronted with these two options, they end up at least sort of saying, yeah, I guess I'd rather do that than the other thing. For what it's worth, if you go the if you go the polynomial division route, your answer will look a little bit different. It's actually just a matter of the constants that show up, which you can technically absorb into the plus c. That's a bit technical for Math 115 though, so don't stress too heavily about it. All right, 2 examples down, 1 more to go for this particular video. All right, this is the one right underneath the one we just did, and it's probably the next trickiest of the bunch. Again, just kind of, because of algebra. So we're actually going to do a little bit of legwork before we try to make a substitution here. Just as a heads up, remember we've got this x cubed living inside a logarithm. Our properties of logs say we can haul that sucker out front of the log. So I'm going to do that just to clean this up. That leaves a 3 down here in the denominator. Yeah. I can write that out front as a 1/3. Remember, it's in the bottom of a fraction, so that's where we need to put it. Okay. Now, in terms of substitutions here, you might say, well, I want to grab the denominator. Have at it. It's not going to end well, because if you set u equal to x natural log of x, the du requires the product rule, right? Because you got two things multiplied together. And yeah, nothing like that shows up here. It doesn't go so well. Again, this is where sometimes you kind of have to play around with it. Here's what I'm going to do this time around. Let u be ln of x. You might be saying to yourself, well, that leaves that x right there. How's that going to help us out? Well, remember, what do we do after picking a u? We find the du. Du is, hopefully you recall, the derivative of the natural log function is 1 over x. Yay! There's an x. I could rewrite this as like 1 over x times this thing. It's almost like Professor Carroll planned it that way. All right, done being snarky. Anywho, so we still got the 1/3, 1 over x dx. That becomes my du. And 1 over ln of x leaves me with 1 over u. Yep, and the antiderivative of 1 over u, as we've seen already, 1/3 ln absolute value of u plus c. And yeah, now we back substitute, and it looks kind of strange. Bear with me. Ln of ln of x. I want a function of x. So yeah, that's how we'd write it. Don't try to collapse that as like ln squared or anything like that. It's 1/3 ln of the absolute value of ln of x plus c. So yeah, those are the two trickiest problems on here. I want to take a look at some of the examples on the next page of the worksheet, though. The good news is we're actually kind of over the peak in terms of difficulty for this stuff right now. So keep on watching. Got another video coming up in just a moment.